In this lecture, we look specifically at sinusoidal waves. Here we see the blue waveform, a sinusoid that has a displacement in the y direction and it extends in the x direction. That's the sinusoid. First, we'll consider the wave without propagation. That is, that y is equal to x with t equals 0. So at time t equals 0. So the waveform is stationary. In that case, the y is just equal to some amplitude a times the sine of kx, where k is the wave number. Lambda is the distance for one full cycle. So when x is equal to lambda, then k times lambda is equal to 2 pi. So the wave number k is equal to 2 pi divided by lambda. Now we have propagation to the right, so we actually have a time dependence. So our blue curve now is moving to the right. In this case, now the amplitude is the same, it's still a sine, and we still have a kx, but you also have the k is also multiplying a minus of velocity times time. The velocity of the wave. The velocity of the wave is propagating. If we wanted the wave to propagate to the left instead, we've changed the minus sign to a plus sign. If we set at one point, for example, the origin, so y is equal to x equals 0, comma t, then our waveform would be the amplitude times the sine of minus k times the velocity times time. T is the time for one full cycle to pass the origin. So when t is equal to this capital T of the period, then k times the velocity times the period is equal to 2 pi. So the propagation velocity v, if we solve that, is equal to 2 pi divided by k times the period, which is equal to 2 pi divided by k is lambda. So a lambda divided by the period. And also, so kv is equal to 2 pi over t, and that's equal to omega, the angular frequency. So there's many different ways of writing this, relating these different constants describing the wave, the wave number, the angular frequency, the period, and the wavelength. So that the standard way of writing the full solution for this sinusoidal wave is y as a function of x in time is equal to an amplitude times the sine of kx minus omega t. Let's look at an example with ultrasonic waves. The ultrasonic waves used for medical imaging have a frequency of around 8 megahertz, and the velocity of the waves in soft tissue is around 1500 meters per second. How small a feature can it image? The source of resolution of any imaging is roughly the wavelength. So omega is equal to 2 pi f. That's equal to 50 times 10 to the 6th radians per second. Omega is equal to the wave number times v, or the wave number is then omega divided by v. So that's 50 times 10 to the 6th radians per second times 1500 meters per second. Gives us a wave number of 33,500 inverse meters. K is equal to 2 pi over lambda. So lambda is equal to 2 pi over k, which is equal to 2 pi divided by 33,500 inverse meters, which gives us, this is equal to 0.19 millimeters. For comparison, a human hair is about 1/10 of a millimeter, and an optical microscope can image features of around 0.0005 millimeters, or half a micron. So the ultrasonic imager can see something that's about twice the thickness of a human hair.